All right, since it's 2, we're going to go ahead and begin. If you are paying attention, please type the word "here" into the chat so that I can use that to check. Thank you all. So today's lecture is going to be fairly brief. We are going to be talking about resistor combination techniques. Let's start by looking at resistors in series. So let's consider a network where we have a voltage source, like so. Vs connected to multiple resistors that are connected in series. So let's call this resistor R1, this resistor R2, all the way out to some nth resistor R sub n. Like so. This is an example of a single loop circuit. And what I mean by that is all of the elements are connected in series. Since all of the elements are connected in series, they all share a common current, which I will label I. Using Ohm's law, we can express a voltage drop over each of these resistors. So let's call this VR1. Let's call this VR2. And finally, let's call this guy out here to the right VRN. So what I'm going to do first is I'm going to write a Kirchhoff's voltage law equation where I'm going to say negative Vs plus VR1 plus VR2 all the way out to the voltage drop over resistor Rn, VRN is equal to 0. And then I'm simply going to rearrange this very slightly by moving the Vs term onto its own side of the equal sign. And from this, we will observe that the source voltage Vs is equal to the sum of the resistor voltage drops in our simple circuit. I can then express each of these resistor voltage drops in terms of our common current I using Ohm's law. So for instance, VR1 would simply be I times resistor value R1. VR2 would be I times resistor value R2, and so forth. All of the terms on the right-hand side of the equal sign all have a factor of I, so I'm going to simply factor that out. So that we will have I multiplied by a factor of R1 plus R2 all the way out to R sub n. And I'm going to call this sum of resistances REQ, comma S. representing the equivalent series resistance seen by our voltage source, right? If I divided both sides of my equation by I, so that I have the ratio of V over I, that is simply the resistance or the equivalent resistance that the voltage source sees, where Req, comma S is simply R1 plus R2 plus all of the resistors out to R sub n. So whenever we have resistors connected in series, we can simply add them linearly. Okay? And we're able to do this because of Kirchhoff's voltage law. I can put this in a more succinct mathematical expression. The equivalent resistance of resistors in series is simply the sum from I is equal to 1 to n of R sub I. Does anybody have any questions regarding combining resistors in series? All right, let's move along to combining resistors in parallel. So in this case, we are going to consider a single node pair circuit, or a circuit in which all of the elements are connected in parallel, where we have some current source, IS, that is supplying current to a network of parallel resistances. So let's call this guy R1, this guy R2, and this guy out here, R sub n. Since all of these elements are connected in parallel, we will have a common voltage, which I will label V, and I am arbitrarily assuming the positive polarity terminal of the voltage will be on top, and the negative polarity voltage will be on bottom. And from this, we should observe several resistor currents. So there will be a resistor current IR1 flowing down through resistor R1. There will be a resistor current IR2 flowing down through resistor R2. And there will be a resistor current IRN flowing down through resistor RN. If we apply Kirchhoff's current law at the top node using formulation number 3, where currents that are leaving the top node are considered to be positive, what we will have is a KCL equation that looks something like this, where we have negative IS plus IR1 plus IR2 plus all the way out to IRN is equal to 0. I'm going to move my current source term to its own side of the equal sign, leaving me with IS is equal to IR1 plus IR2 plus IRN. And then I'm going to use Ohm's law to express all of these resistor currents in terms of the common voltage V. So we'll have V over R1 plus V over R2 all the way out to V over Rn. Since all of the terms on the right-hand side have a common factor of V, I can move that out. And I will see V multiplied by 1 over R1 plus 1 over R2 plus 1 over Rn, or V divided by Req comma P, where Req comma P is the equivalent parallel resistance. Nothing more than the ratio of V over IS, which comes out to be 1 over R1 plus 1 over R2 all the way out to 1 over R sub n, and all of this to the -1 power, or simply the reciprocal of the sum of the reciprocals of the resistors in parallel. Okay. In a more succinct mathematical notation, Req comma P looks like this. So we'll have the sum from I is equal to 1 to n of 1 over R sub I. And then we take the reciprocal of this summation. So this is how we combine resistors connected in parallel. Now I want to point out something interesting. Let's consider a network containing exactly 2 resistors connected in parallel. So we'll have a resistance R1 here. And a resistance R2, like so. Let's call this terminal A and terminal B. If we were to look in to this set of terminals, so we're trying to find some resistance RAB, what we would have is RAB is equal to 1 over R1 plus 1 over R2, according to the equation that I developed a few minutes ago. What I'm going to do now is do some simple algebraic manipulation of this expression. So, for instance, I could multiply the 1 over R1 term by a factor of R2 over R2, and I could multiply the 1 over R2 term by a factor of R1 over R1. In doing this, what I get is 1 over R2 divided by R1 R2 plus R1 over R1 R2. Since our fractions in the denominator have a common denominator, we can lump these guys together such that we will have 1 over R1 plus R2 divided by R1 times R2. And we have 1 over a fraction, so we can simply take the reciprocal of the fraction and see that the resistance seen between terminals A and B simplifies to R1 times R2 over R1 plus R2. This result is a handy shorthand method that allows us to very easily and quickly calculate the equivalent resistance of two parallel resistors. I want to point out very specifically, though, that it only works for exactly two resistors. We can force it to work for three resistances by combining two resistors in parallel and then combining that equivalent resistance in parallel with the third resistor. So what I mean by that is, let's work a quick numerical example here. Let's say that I have a network where I have an 8 ohm resistor, a 12 ohm resistor, and a 20 ohm resistor. And I want to find the resistance seen looking into terminals A and B, RAB. We should know right off the bat that we could express RAB simply as 1 over 8 ohms plus 1 over 12 ohms plus 1 over 20 ohms. And using my calculator, I get an equivalent resistance of 120 over 31 ohms, which is the same as 3.871 ohms. Alternatively, we could calculate a quantity, let's call it RAB prime, that's just R1, the 8 ohm resistor, and R2, the 12 ohm resistor in parallel. So that's going to look like 8 ohms times 12 ohms over 8 ohms plus 12 ohms, which comes out to be 24 over 5 ohms, or 4.8 ohms. And then we will combine this resistance RAB in parallel with our 20 ohm resistor, so that RAB is 4.8 ohms times 20 ohms over 4.8 ohms plus 20 ohms. And we get 3.871 ohms. So we got the same result either way we approach this, okay? Typically speaking, when I have exactly two resistors, I use the shorthand method, and whenever I have more than two resistors, I rely on the reciprocal based relationship. All right, so any questions regarding combining parallel resistances? All right, so the last thing that I would like to do today is to explain to you how I handle determining the equivalent resistance of complicated resistor networks. I'm going to do this by working a portion of one of your web work problems. This is homework set number 3. problem 2. And in homework set homework set number 3, problem 2, we are given the following network. We have a 100 ohm resistor, a 25 ohm resistor, a resistor diagonally here, which in the schematic diagram is labeled as R4. And for my random set, R4 has a value of 36 ohms. So I'm just going to put that in here. We have a resistor R2, where for me, R2 is 135 ohms. We have a 50 ohm resistor here down the middle. We have a resistor R1 here, which has a value of 96 ohms. We have a resistor of R3 diagonally across the bit here, having a value of 300 ohms. And then we have a 75 ohm resistor and a 200 ohm resistor. So when we are told that we have a node C in the top left corner of our circuit, a node B in the top middle, a node A on the top right, and finally a node D on the bottom middle. Okay. I am going to go about solving for the resistance R, A, D. So how I go about solving a problem like this is the first thing I do is identify my nodes. So this node in the top left will be node C. This node in the top middle will be node A. This node on the top, node in the top middle will be B. The node on the top right will be A. This node on the bottom middle will be D. And I have 2 additional nodes that were not given a label in the problem statement. This guy on the bottom left, which I will label as E in a moment, and this guy on the bottom right, that I will label as F. So here's E. Here's F. So after I have identified and labeled all of my nodes, what I like to do is effectively spread the circuit out and play connect the dots with resistors. So since I'm looking for the resistance between terminal A and terminal D, what I'll do is I'll put terminal A on one side of the page and terminal D on the opposite side of the page. And then I just figure out the different ways that I can get from A to D. So for instance, I can go from A to D directly through the 300 ohm resistor. So I'm going to put a 300 ohm resistor here in the middle that directly connects node A to node D. And I'm also going to put a little check mark by the 300 ohm resistor so that I recognize that I've already included that particular resistor in my new model. Another way that I could get from node A to node D would be to go through node F. So I can go from A to F through the 75 ohm resistor. And I can then go from F to D through the 200 ohm resistor. And I'll put a little check mark by both of those. Another way that I could go from node A to node D is to go through node B and then to node D. So I'm going to put a node B here in the middle. And I can go from A to B through the 96 ohm resistor. And I can go from node B directly to node D through the 50 ohm resistor. And put my little check marks by these two resistors. Now, once I go from A to B, there are a couple of different paths that I can use to go from B to D, right? I have that direct path through the 50 ohm resistor that I've already taken into account, but I could also go from B to C to D. So I'm going to put node C here. And when I go from B to C, I go through the 135 ohm resistor. Goodness, moving my screen around too much. And I can go directly from C to D through the 36 ohm resistor. I'll check those guys off. When I hit node C, I actually have a different path that I could take to go to node D as well, right? I could go from C to E and then to D. So I'll put E right here. To go from C to E, I go through the 100 ohm resistor. And then to go from E to D, I go through the 25 ohm resistor. If I'm not mistaken, all of my different resistors are accounted for. So this redrawing of this resistive network physically takes up a lot more space, but to me, it's a lot easier to interpret how to do the combinations. So for example, we can easily see that the 100 ohm resistor and the 25 ohm resistor are connected in series. So that means we can replace them with a single 125 ohm resistor connected between nodes C and D. So I'm going to do that now. I'll make these changes in blue. So I'm combining 100 in series with 25. So that's going to look like 125 ohms. Well, now I can see that the 125 ohm resistance is in parallel with the 36 ohm resistance. So I'll take 125 times 36 over 125 plus 36. And I can replace this resistance between C and D with a parallel resistance. So let's delete this and delete this. And when I make that combination, I'm left with 4,500 over 161 ohms. I can see that this 4,500 over 161 ohm resistor is in series with a 135 ohm resistor. So I can combine them together to make a single resistance. Which is going to look like 26,235 over 161 ohms. And I can see that this new equivalent resistance is in parallel with my 50 ohm resistor. When I make that combination, I get a 38.260 ohm resistance. And I can see that this 38.260 ohm resistor is in series with the 96 ohm resistor. So I'll simply add 96 to that number, and I get a 134.260 ohm resistor here. I can see that the 75 ohm resistor and the 200 ohm resistor are in series. So that's going to look like 75 plus 200 is 275 ohms. And now between terminals A and D, I can simply see three resistances in parallel. So I can say that RAD is 1 over 300 ohms plus 1 over 275 ohms plus 1 over 134.260 ohms. And I'll throw this into my calculator. And the equivalent resistance between terminals A and D comes out to be, I can write here, 69.358. Oh, I have been combining resistances for quite some time at this point. And in my opinion, this is the easiest way to combine a complicated resistor network. It is a very formulaic and at times tedious approach, but utilizing different colors to identify your nodes and kind of spreading things out and then working your way from the bottom to the top seems to work for me very well. There are other different resistor combination techniques that are out there, but this is the one that I find benefits the way that I think the most. So I just wanted to make sure that I shared that with you all who may struggle with resistor combinations. So unless there are any questions on this, this is all that I had prepared for today. All right, I'm not hearing any questions. So I hope you all have a great weekend, and I will see you on Monday. I am actually going to shut the Zoom call down a little early today so I can go across the street and help with the freshman advising and registration, the orientation stuff. I will be available via email this afternoon, as well as anytime tomorrow or over the weekend, if anybody hits any questions. Again, hope you guys have a great weekend, and I'll see you on Monday afternoon.